Hi, this is Joe Severs with my capstone presentation on the state of Montana. State motto, Oro y Plata, gold and silver. Montana is our 41st state. It's the fourth largest state. It's in the northwest. Capital, Helena. I've had the pleasure of being in Montana. I was there 2 years ago. This is a picture south of Missoula, facing west. It's the Bitterroot Mountains. This is June. Still snow on the mountains. Not too far away, Lewis and Clark Campsite Travelers Rest. Lewis and Clark stayed there twice, once heading west, once heading east. But on to geology. We're going to talk about Montana, a big state with dozens and dozens of formations, which I'm going to simplify and discuss the sedimentary formations in the east and the orogeny in the west. Here's the big detailed map of Montana, and there are, as I mentioned, a lot of formations, especially in the west. Here's a close-up of the lower southwest corner. You can see how crowded and tiny so many formations are. Makes it hard to come up with a big picture, but we're going to try. Here's a simplification of the physiographic features of the state. As alluded to before, mountainous on the west, part of the Rocky Mountains from northwest to southeast, more level to the east. In order to discuss this, I've taken the liberty of simplifying my hand drawing here as to some of the major formations, at least some of the major ideas or considerations to think about Montana. I want to draw your attention to the east, where we have some major formations. K is Cretaceous, T is Tertiary. Those are among the more recent formations. So you can see a K, a T, a T, a K, a T, a T, a K, a K. Here's a Q, Quaternary, which is even more recent. In the west, we have Ks for Cretaceous. We have Ys for Middle Proterozoic. We even have, and I'll discuss this a little later, an A, that's Archean, among the very oldest kind of rocks. Largest formations in the east are from relatively recent periods, as I just mentioned, Cretaceous, Tertiary, even a Quaternary formation. Western formations, also much older, also sedimentary like the east, but also a few igneous formations, and there's many more of them. So let's discuss, compare and contrast the arrangement. I created this plot based on my experience, 40 years in statistics, to try to quantify the jumble of formations, ages of formations in Montana. So what I've done here, I started on the 48th parallel, moving east, recording any given formation, what period it comes from. So we move from the west all the way to the east. And I hope what you see is clear is that even in the west, we start out some older rocks, Proterozoic, and then suddenly, a few miles in, we find a jump to the Cambrian, then we're back to Proterozoic, then a jump all the way to the most recent Tertiary and Quaternary Proterozoic. As we travel farther east, we find younger rocks in the eastern half of the state, formations dating to the most recent, the the Cretaceous, Tertiary, and Quaternary periods. How did Montana get here? My summary is briefly, Montana was underwater a lot. That's why you have sediments in the east. Orogeny in the latter part of the Phanerozoic era. So let's consider the Silurian period. Montana would be here underwater. Late Devonian, underwater, shallow. Note also the equator believed to be here, so it would tell us that it was warm, shallow water and marine environment there at the time. Late Mississippian, the Carboniferous, which is in the Carboniferous period, still shallow, still wet. Although in the late Carboniferous, the ancestral Rocky Mountains comprising the Front Range and Uncompahgre Range create our orogeny that happens. They are elevated, but then they are worn down by erosion. The Rocky Mountains will come later. In the Permian period, we have a volcanic arc out to the west. I understand this to be as the Pacific plate is pushing under the North American plate. There are possible glaciers, notwithstanding the picture of possible glaciers in the late Paleozoic. The consideration for glaciers is the extensive deposition of loess, wind-blown sediment over Wyoming and large parts of Montana. Loess, this fine silt or dirt, would come from the grinding of the glaciers, grinding down rocks to very fine particles. Then presumably the great glaciers melt, move away, and the loess is blown over their area. Triassic. Montana is starting to come out from underwater. We still have volcanic arc, but substantial parts of it are now above sea level. But in the late Jurassic, it's underwater again. Now we have the Sundance Sea, which is shallow. Late Jurassic, still underwater, although parts of it are above water now. But still, the idea is sedimentary deposition underwater. Now we get to the Cretaceous period, and now we have another round of orogeny. The Cordilleran mountain building begins. I believe, as we discussed in class or in the lecture, this is considered to be unusual. The thinking is that the Pacific plate moved under the North American plate, but a very shallow angle, and such a shallow angle that a lot of the mountain building occurred not at the plate boundary, as would be typical, but far away from the plate boundary. The Laramide, you also have from this plate boundaries, the subduction, that it's such a shallow angle that older rocks are pushed up and over and through younger rocks. Remember my little graph before, a little southwestern part of Montana had Archean rocks right around, mixed in with much younger rocks. This would be a schematic drawing of how it might happen, that the rocks have been pushed and shoved up through younger rocks to the top to where they're exposed. By late Paleogene time, uplifts resulting from the Laramide orogeny have been largely subdued by erosion, which set the stage for the Neogene events that produced the Rocky Mountains. In other words, the Laramide orogeny did not create the Rocky Mountains. The Rocky Mountains came later. The Eocene volcanics, again, discussing the very low angle of subduction, creating an orogeny far away from the plate boundary. So now in the Neogene era, more typical of what we see in Montana, mountain ranges in the west, relatively less so in the east. It would be no surprise then when we look at a map of the major faults in Montana to see extensive faulting in the west, extensive parallel or somewhat parallel in the west, where all this mountain building is taking place. Certainly notable faults in the east or the center, but very distinctive parallel pattern consistent with a lot of rocks being shoved, in this case from southwest to northeast. Finally, the last stage that I'll discuss in Montana's history, the Neogene Ice Age. Glaciers coming over part of Montana, not completely, but certainly substantial amount of Montana was covered. When we say ice sheets, how thick are we talking about? One of my favorite XCTD cartoons comparing the thickness of the sheets against modern cities. These are western and central cities, not Montana, but I think it's useful for giving the scale of the idea of the enormity of these sheets and how thick they could be Even in Montana, you would expect that certainly tens or dozens of meters tall on top of the ground. So having seen that Montana can be split into the sedimentary east and the Rocky Mountain west, it should be no surprise then that the two biggest industries in Montana are mining and agriculture. Thanks.